Is it rolling?
Yeah. Yeah, it is.
Okay, thanks. Hello, Calgary. My name is Konrad Gierus, and I am the proud founder and CEO of Pong-Bot. Today, I'll be taking you through the steps that I took to make my robot. I'll also be taking you through the problems that I ran into on the way and how I managed to fix them. And finally, I will show the robot in its full glory. It beating me in a game of Pong. Live action, that is. Using the software OpenCV, I was able to detect the ball being neon yellow and the paddle being pink, and applying simple logic to figure out if the ball is on the left or on the right side of the paddle. And then I could send that information to the motor and move the paddle left and right accordingly to find the ball. OpenCV is a computer vision library that I used for object tracking. I first pulled frames from my camera and found the largest masses of colors that was neon yellow and pink. Using that information, I could find their bounding boxes and centers. I then used that information to calculate their relative positions. The first start of this program is what I like to call the processing stage. It sets all the information, so if you don't give any information, it already has that information stored in there. It also makes a rectangle around all the 4 desirable objects, which are the ball, the paddle, and the 2 boundary sticks, which is the finding stage. I essentially give it the range of colors that I think will be best described as them, and it finds those colors, anything within the range, and sends it to the processing stage, which then puts a rectangle around them. So when it finds those 4 desirable objects, it sends them to the processing stage. The final stage of this process is called the command stage. And the command stage is essentially putting it all together, sending the actual go or no-go to the motor. So say if the ball is on the left of the paddle, just like that, it would tell the paddle or the motor to go left, because then the paddle can catch the ball. So as an example, we have the situation where the paddle is on the right side of the ball. So as soon as the computer detects that, it will send a signal for the paddle to move left. And when the computer detects that the ball is overlapping with the paddle, then it will send a signal for the paddle to stop moving, thus allowing the ball to be intercepted by the paddle. So these posts are here to stop this paddle from breaking itself on either sides of the contraption. We had to implement this because when the ball rolls off, then the paddle follows with it and breaks itself on either side of the contraption. So how did we do this? Well, the program finds the 3 largest pink pieces of paper, the largest being the paddle, and the second 2 largest being the post number 1 and post number 2. And when the paddle tries to go past one of the posts, then the program sends a signal to stop it and won't allow it to break itself. So what we have here is the non-powered side of the machine. So we have here is the rollers, and this is here because the webbing had too much. It touched too much of the paddle, and so we couldn't have that. So we added these rollers to keep the webbing above the paddle. Here we have these guides. It's here because the webbing was falling off the pulley too often, so we needed some guides, and yeah, that's been on powered side. So here we have the motorized side of the whole robot. So as you can see, we have this this motor that came from a toy truck, remote-controlled truck, and I had to take the toy apart and attached it to the motor controller. And over here we have this little stopper, because sometimes this pole didn't work as I intended it, and so it stops the paddle from running off the track. And so here we have this smaller 2x4 that lets me mount the motor on and this spark from red board on without wasting any space on this larger track. After I built the robot and programmed this program, then I decided to test it. I tested it quite a few times. The first test that I did was if it truly worked. And so the way I did this test is if it caught I just threw this ball in a random direction, and if it caught it, then beautiful, it's a success. The overall accuracy of my robot is around 70% success rate. That's a 30% fail rate on the first serve. When you compare that to the average 12% fail rate of ping pong, we are actually doing pretty bad. The other test that I did was a speed test. How far did this travel and how long? So, for that, I put the ball in the middle of the table and tested how long it would get to get to the ball. For this, it was 1.799 seconds. All of this speed test translates to the paddle can go around half a meter per second. Now, if you compare that to the whopping speed of Andrew Bagolet's serve, which is 31 meters per second, ours is not going to cut it. In conclusion, I think this robot did everything it set out to be. It set out to put a paddle in front of a ball. Now, whether that paddle was a piece of plastic or an actual ping pong paddle doesn't really matter. This was a success unto itself. I got to learn how to program almost from scratch. I also got to learn how to overcome the challenges of building a robot. Every little piece can make the entire thing go down. But like everything, it needs improvements. Number one, it would be amazing to have it move up and down. Number two, it would be amazing if I could actually put a paddle on here instead of this light piece of paper. Number three, replacing this motor with a stronger version would be very good. Number four, I need it to go way faster than it is already. Number five, it would be amazing if this could have different types of shots, like the swirl shots and just the slam. It'd be great if I could fold this up, hide it in a suitcase, and go to the ping pong championships. Bye.